Hello, this is the walkthrough for paper 5. I'm actually going to use the February-March 2019 paper for this walkthrough, but you could use almost any for demonstrating how to tackle paper 5 because they're quite formulaic. They follow pretty much the same scheme every time. It's just the numbers are different, the context is different, and the physics underlying it may be slightly different, but actually in terms of what you actually have to do, it's pretty similar every time. So you'd start obviously by putting your name, and then you'd tackle your first question. Now you notice that there's no formula sheet here, so we're going straight into the questions. A student is investigating the behaviour of a capacitor circuit shown in figure 1.1. You've got a neon lamp flashes on and off when it's connected across the capacitor with a potential difference VF of approximately 90 volts. The student has a number of unmarked resistors, so they don't know the resistance to it. It is suggested the period of T flashes period T of the flashes of the lamp is related to the resistance R of the resistor by this expression, where T is RC where K is a constant and C is the capacitance of the capacitor up here. Constant C is given by VI minus VL over VI minus VF, all in brackets, natural log of it, where VI is the potential difference across the input, VF is the potential difference required to make the lamp flash, and VL is a constant. Okay, so design a laboratory experiment used to test the relationship between T and R. Explain how your results could be used to determine a value of K and VL. So you should draw a diagram on page 3 showing the arrangement of the equipment. You need to pay particular attention to the procedure being followed, the measurements being taken, the control of the variables, the analysis of the data, what you do with the numbers, and any safety precautions. Right, so first thing to think about is what's key here. Well, the key parts here are the idea that you're investigating relationship between T, the time period, the time period of the flashes of the lamp, and the resistance. So resistance is something that you can set, so that's your independent variable, and the thing you're trying to measure is the time period. Okay, now you've got to think very carefully. So explaining results could be used to determine K and VL. So we've got to start thinking about what it is we're actually doing here. Well, we've got to think about it. If we're changing R to measure T, what have we got to keep constant? Well, we can tell straight away that that capacitance must be kept constant. That's going to be our major control. And then we have to think about how we'd actually collect the data. So first of all, we've got to think about how this is going to work. So we've got to think about a labeled diagram. We've got to think about how the DC power supply would be positioned, a neon lamp, where we'd put the neon lamp, and some method of measuring resistance of the resistors. So I've got to think carefully about how we'd actually do this. So what we've got to think about a little bit here is what we're actually measuring. So the first thing, let's go for our low-hanging fruit. We know that R is the independent variable. It's the thing you measure. Okay, we know that T is the dependent variable, the thing you'd actually be finding out. So the independent variable, remember, is the thing you deliberately set. The time period, the dependent variable, is the thing you actually measure. That'd be the time period of the flashes. We'd have to then start thinking about what we need to keep constant. We keep the capacitor oops, capacitance constant. Okay, now before we've even tried to think about the circuit diagram, because we're actually thinking about the circuit diagram might be quite difficult, so we've got to think carefully about what we're actually plotting a graph about of. It says it wants you to find the relationship between T and R. So all this other stuff you don't really need. What you can do is you could then use to talk about how we find K and VL. Well, if we think about it, T is equal to RCK. So if T is equal to RCK, we can slightly rearrange it, because we know where K is a constant and so is C. So CK multiplied by R. So we know that if we put time period on the y-axis, the time period for the flash on the y-axis, we end up with the gradient multiplied by the value of x, R on the x-axis. So we know that what we want to do is take several measurements of time period for lots of different measurements of resistance. So that's what we say. Notice I haven't even started doing things like circuit diagrams yet. So take several measurements of T for several values of R. There we are. Okay, and we would draw a graph of, well, it'd be T on the y-axis versus R on the x-axis. That's pretty easy so far. So what would we get? Well, we know there's no plus C element here, so it would be a straight line through the origin. So you would obtain a straight line through the origin. This is the kind of stuff that's the same for almost every paper, so it's almost the same. Sometimes you have to think about an intercept, but basically you're looking at drawing a straight line graph. So obtain a straight line through the origin with a gradient equal to CK. Okay, now quick check, does it tell me that the capacitance is known? Well, it says near lamp flash is connected across the capacitor with a potential difference VF. Doesn't say it's known, but you can assume it's known, can't you? So we're going to assume that that's known. We're going to assume that we know it. So K equals, well, if that's equal to the gradient, then K is going to be equal to the gradient divided by C, if we know what C is. Okay. So there's lots of other things we can do here. We can always work out what K is, and well, we're given a formula, aren't we? Notice I've not even looked at the circuit diagram yet, because the circuit diagram for this is probably not going to be that easy to think about. But we've got pretty much everything here so far. So what we're doing next is we're thinking about how we then obtain a value. It says it wants a value for LVL. Well, we're given a formula, so we could then say that since, and we're just literally going to quote this formula. Okay, but then rearrange it, see if we can rearrange it to make VL the subject. So since K equals VI minus VL VL over VI minus VF, natural log of it. Okay, then it stands to reason that it's going to be e to the power of k. Whoops. E to the power of k, remember k is something we've worked out from the gradient, is equal to VI minus VL over VI minus VF. Okay, so we'd then just rearrange the formula to make VL the subject, so it's going to be e to the power of k multiplied by VI minus VF equals, whoops, VI minus VL. Okay, so I want VL to be the subject, so we're going to make it, and we're going to subtract that from both sides and then swap the signs over. So it would be equal to VI minus e to the power of k multiplied by VI minus VF equals VL. Okay, or something along those along those lines. So we'd find k from the gradient. Okay, and that is basically how you do it, but we haven't actually thought about the practical side of things yet. So I'm just going to find just looking for my ruler there, sorry about that little pause. Where was I? Yeah, so we found a way of finding VL. We can find k from the gradient, but the only thing I haven't really thought about is how we can actually do the experiment. Remember, you're not really going to do it, but they want a circuit diagram basically, because it's an electricity experiment. You need a circuit diagram. So all you've basically got, if you look at the actual brief of the question, you're given an input, you've got an R and got a capacitor there. You'd put your neon lamp across the output, I think, by the looks of it. I think that's about right, because it says it's connected across the capacitor with a potential difference of VF. Across the lamp is of approximately 90 volts. Okay, so basically when it reaches 90 volts, the lamp discharges the capacitor, which then recharges again. So what we can do is we can think about how we go about drawing that. Well, it's pretty similar to the initial circuit. So I've got my resistor there, I've got my wire, there's my output. Like that. You've got your capacitor would go across here somewhere, like that. And we know we're going to have our resistance here. Put a capacitor in place. Notice I'm using a ruler. A ruler just makes it a lot easier to draw a diagram in a way that's clear and easy to understand. So we're almost there. The only difference is I'm going to close this up a little bit, and I'm going to suggest a DC supply direct current, approximately 100 volts, let's say. Okay. I don't think they're actually going to want that particular detail, but you know the potential difference across here has got to get to about 90 volts before it'll flash. So we've then got our output. Now our output's going to comprise of two things. The first thing is the neon lamp. Now we're not expected to know any special symbols for gas discharge lamps, so we're just going to use a standard symbol for a lamp and label it neon lamp. That way an examiner looking at that paper knows that it's a neon lamp. And we've got to find some way of measuring the voltage across it, because in order to find the in order to be able to find the value for the capacity, the value for V and the value for we've got to find the voltage across it. So what we'll do is we'll connect that to a different kind of meter. We're going to connect that to an oscilloscope. Okay, now that's roughly what it would look, what the circuit diagram would look like. We've just got to remember to label it. Just going to be very, very clear. That's capacitor C, that's resistor R. Okay, because I refer to R and C in the actual in the response, so I better use it in the diagram here. The other thing that's complicating this is they say unknown resistors. Now the examiner clearly has gone out of their way to say unknown resistor. So what they want you to do is to think about some way of measuring the resistance. It's not going to be enough to say to just connect it to a multimeter ohm meter and measure the resistance. They obviously want something a little bit more than that. So the simplest way to deal with that is to remember that old GCHC experiment for measuring resistance, which is going to be the by setting a voltage across it with a battery. We're going to call it V. Doesn't matter what the voltage is particularly. Well, it's within reason. And we're going to take our resistor. How she blows. And when you're measuring the resistance of a resistor, remember you measure the voltage across it. You don't just trust it to be the EMF of the power supply. That would be incorrect. What you'd do is you'd connect together a voltmeter. And to measure the current through it, you would connect an ammeter in series. This is very, very basic. And I'll put it on here that R equals V over I. Okay, so that's how we get R. So what I've done there is I've drawn a circuit diagram. I've explained how we're measuring the resistance. The next thing to think about is all the sort of the additional bits. Because we've got the basic bare bones of a plan here. All we've got to do now is think about how we actually get values. Okay, so the first things, there are various things to think about in here. It does brief you the procedure to be followed. Well, I've kind of shown the procedure, but I just need to highlight a few different things. So we've got to think about, really we're thinking about how we measure these values. Okay, so we would need to say to find R. Well, I'm going to do a little shortcut here. I'm going to call this A. I'm going to call this B. So I could say to find R, assemble circuit B. Okay, I even draw a ring around it. Assemble circuit B. Measure the current and PD, potential difference, and we know that R equals V over I. I've already said it in the question, but no harm putting it here as well. So that's how we find R. What else have we got to find? We've got to find the capacitance. How do we find out the capacitance? Do we do a big discharge? Do we do lots of discharge curves? Do we? Is there some special gadget? Nope. We read it from the side of the capacitor. All the capacitors are labelled. So we say how we know it. Okay, we read from the side of the capacitor. So what else do we need? We need to find, if we're looking at this, we need to find the time period. Well, if you think about it, if we're looking at, if we're looking at the oscilloscope screen, we know that what's going to happen is the voltage will go up. When the voltage reaches 90 volts, it will discharge, so it will go down again. So we're looking at an oscillating voltage, and that will give us the frequency of the flash. Okay, so to find T, we would read it from the oscilloscope. So to find t, would read it from the oscilloscope. Well, it would be the reading would sort of show it going up and then down and then up and then down and then up and then down. We know that that distance on the reading would be x, and we know that the time period would be equal to the distance between peaks distance between peaks multiplied by, of course, the time base, which would be x times time base. Okay, so we found t. So what else do we need to know? Well, if we could, what else do we need? We need to find VI, the input voltage, or VI is the input voltage. Well, that's going to be the maximum value on the oscilloscope, and then it tells you what's VF. It tells you that VF is the potential difference required to make the lamp flash, and VL is a constant. Okay. Okay, so we could use the oscilloscope to find VF and VI. Because don't forget, it is a voltmeter. And it's going to be the height of the sort of the peaks multiplied by the gain. Right, now have we addressed everything? So we said how we're going to measure everything. We've said what we're controlling. We've said how we're going to analyze the data. The last thing on here is safety precautions. Now, the big thing about safety precautions is you don't put in stuff that's not relevant. So in this experiment, you know, if you say something like wear goggles, you're not going to get the points. So maybe you want to think about safety. Let's think about safety. Well, what's going to be dangerous here? If it's got 90 volts, you could get an electric shock. So first thing is switch off between readings. And we could say we could wear insulating gloves. Not thermally insulating, we mean electrically insulating. But it's no good to just say what you're going to do. You've got to say why you're doing it. Well, it's to prevent electric shock. Okay, and that's about it. I think about the only thing you could possibly think of to add on to that, if you were feeling adventurous, is you could start talking about how you can perform some form of preliminary experiment to make sure you've got a readable value of your time period. Obviously, if you're trying to measure time period of 15 seconds using an oscilloscope, you're not going to be able to do that. You might want to work visually. And actually count, and sort of count the number of flashes a minute or something like that. Or you might just make sure you're setting a reasonable value of C and R to give you a good time period. It's about trying it out. So that is the basic method for question 1. So let's summarize exactly what do you need to do. You start off with setting your variables. You look at your independent and dependent variable. You find that by reading the brief. It says design laboratory experiment to test the relationship between T and R. It could be X and Y. It could be A and B. If you've got that, you've got to think about what it is you can deliberately change and what it is you've got to measure that changes as a result of it. Then think about what's constant. Well, usually it tells you if there's something constant, like a capacitance. Again, we're using this idea that we're keeping C constant. Well, K is just another constant, but it's not it's not one you can actually consciously keep constant, but we know we can always use the same capacitance every time. So that's pretty simple. You then look at what kind of graph you could draw. So think about the formula. Start off with a formula. Rearrange it to make a y equals mx plus c. The key is the m part has to be constants only. Y is what goes on the y-axis, x is what goes on the x-axis, and then you say, you take several measurements. You draw a graph of t, you say which one goes on the y-axis, which one goes on the x-axis. The idea that if it's valid, you get a straight line through the origin with a gradient equal to ck, which means you can find k. You can find that value using the gradient. We know that if that's the case, ck is the gradient. So if ck equals gradient, then k equals gradient over c. You then look at any subsequent calculations you need to make. Don't worry about how you'd measure anything. We've not even started to think about how we measure anything. Okay, we're already about halfway through the marks. So you look at how you'd actually get the value. Always quote the final formula you would use. Okay, then you talk about how you'd find things. Well, how would you find out what the resistance was? Well, you'd make a separate circuit. You draw your circuit diagram. Your diagram, that's a well-labelled diagram, is worth something like at least 2 marks if it's drawn correctly in most cases on that question 1. So draw it correctly, use a ruler, label it. It only takes a minute and it gives you some easy marks. It's very low-hanging fruit. Okay, even if it's only partially correct, you can get some points for it. So we talk about how you find everything. How would we measure R? Well, we've got to put the resistor in a separate circuit, measure the current potential difference. Resistance is V over I. How would we find the capacitance? Well, that's an obvious one. You'd read it. It's written on the side of it. To find T, you could read from the oscilloscope. Now, if you'd forgotten all about oscilloscopes, it tells you it's a flashing light. So you could count the number of flashes per minute, then divide the 1 minute, the 60 seconds, by the number of flashes, and that would give you the time period. Okay, so if this is too complicated for you, think about it more simply. You still get the marks. The fact that you would use an oscilloscope to find VF and VI because they're voltages, and the oscilloscope's essentially a voltmeter. It's height times gain. Be clear about how you're measuring things, and then think about one relevant safety measure that goes in as part of that. Okay, it's that easy, and you can easily score with very little thought and very little actual physics knowledge. You could quite easily score 10 out of 15 without that much effort. So there's really no excuse on that one. It's taken me half an hour and I'm talking at you while I'm doing it. So on to question number 2, and you get all these, you get lots of information here, but remember, you don't have to worry too much about the physics of what's going on. Why? Because really they're looking at your data analysis in question 2. So a student is investigating the motion of a small steel ball in cooking oil. A measure of the oil's resistance to the ball's motion is called viscosity. Viscosity has units pascals, Pascal seconds. The student drops the ball into the cylinder of oil. It says the velocity of the ball is measured when it becomes constant and the viscosity of the oil is determined. The experiment is repeated for different temperatures of oil. It's suggested the viscosity and the Celsius temperature of the oil is given by the equation here, where P and Q are constants. Now you know you've got a power here, so you're probably going to be playing with logs at some point. So a graph is plotted of the natural log of the viscosity on the y-axis versus the natural log of theta, the temperature, on the x-axis. Determine expressions for the gradient and y-intercept. So we've got to think about how we actually do that. Well, if we think about it, we've got to think about the idea that what we're doing here, it says the natural log of the viscosity is on the y-axis. In other words, you make that expression there the subject of the equation. So we've got the viscosity there, so the natural log of the viscosity, now this is log base 10, remember, is equal to the natural log of P times theta to the power of Q. Okay, so what we've got to do is separate out that logged expression there. So you've got two things that are multiplied together, we know we're adding them. So we know that that's going to be the natural log of P plus the natural log of theta Q, theta to the power of Q. So if that's the case, remember if you've got a power, it multiplies outside the log. So what I'm going to do is I'm going to say, well, okay, that's going to be natural log of P plus the natural log of theta multiplied by Q. Okay, so it also wants natural log of theta on the x-axis. Here is our clue. Here is our clue that we're getting it right, because we've got a factor of it here. So what we need to do is put it into y equals mx plus c format. What does that mean? Well, what we're saying is that natural log of the viscosity there, okay, is equal to, now I'm going to swap these over. I'm going to say Q times the natural log of the temperature in degrees Celsius plus the natural log of P. So we now know we can compare the formulae with y equals mx plus c, where q is the gradient, the y-intercept is the natural log of p. So the expression for the gradient is q, the expression for the y-intercept is the natural log of p. It's that easy. Okay, so what did I do here? All I did was I rearranged it to make whatever they put on the y-axis the subject of the equation. Then you try to split parts out so that you've got whatever's on the y-axis, whatever's on the x-axis, multiplied by some sort of constant plus some other constant. Because it tells you in the question that P and Q are constants. So they are constants. So we're going to get we're going to get a straight line graph, but it won't go through the origin. So that's the first bit. Pretty simple so far. The next part is doing the calculations in the table. Now, you don't get a mark really for just doing the calculations. What you get a mark for is for the uncertainties. Now we've got uncertainties in logs. Now when you get a funny expression like a log or a sine or something like that, probably the easiest way to find the uncertainty is to work it out by bounds. But let's do the basic formula first. So if we're looking for the natural log of the temperature or the natural log of 38, well, I don't think we want to go beyond three significant figures. Natural log of 48 is 1.66. That's 1.74-ish. That's 1.81. That's 1.86. And that'll be 1.9. Now careful, it come out to be 1.898. So you have to say 1.90. Okay, a lot of people miss that one out and lose the marks as a result. Do exactly the same here. The log to the base 10 of 41 is 1.61. That's 1.51 because I've practiced already with this paper. The log base 10 of 25 is going to be about 1.4. Hello, 1.40. Log base 10 of 20 is 1.301. So I've got to say 1.30. Log base 10 of 1.7 is 17 is 1.23, and for 14 it comes out to be 1.15. It's not quite 1.1. It's not quite as low as 1.14. So how do we find the uncertainty? Well, what you've got to do is you've got to use upper or lower bound. So I would actually find out what the what the log base 10 of 42 was. It's plus or minus 1, so it could be anywhere between 43 and 40. So I'm going to go for an upper bound. Why? Because it's kind of my habit. So if I go for an upper bound, I know that my upper bound, it would come out to be 1.62. Okay, that's my upper bound. Okay, so if my upper bound is 1.62, my difference is 0.01. Okay, if I look at my upper bound, that log base 10 of 33 would be 1.52. So that then again is a difference of 0.01. My next upper bound would be 25 plus 1 is 26. So the log base 10 of 26 would be 1.41. So again, that's plus or minus 0.01. The log base 10 of 21 there, because I'm adding 1 there to get an upper bound, that comes out to be 1.32. So now our uncertainty is increased. Next one's 17 plus or minus 1, so it's plus or minus 1. It's the difference here is it's 8. There's a log base 10 of 18, gives me 1.25 very roughly, so that's 0.02. And this one here, the upper bound here would be 15, so log base 10 of 15 would be 1.17, so that's plus or minus 0.02. Now it wants me to calculate those values and then plot the graph. So I'm plotting a graph of log base 10 of the viscosity against log base 10 of the temperature in degrees Celsius, and I've got to include the error bars. They must include them. You don't get any marks. Well, you get 1 mark for plotting your points. You get a second mark for your error bars, but without your error bars you can't do the rest, so be careful. So I've got my graph paper here, and I'm going to do this in real time so that you can see it, because I want you to watch and understand exactly how we actually make those range bars. So here's it's the log base 10 of the temperature. So our lowest value is 1.58, so 1.5, 55, 56, 57, 58, and that's 1.61. So that's 1. Goes all up here. 1.6, 1.61 there. So you start off by putting a little cross in place, and then you plot the rest of your values. Now you've got to plot them correctly. If you plot them incorrectly, you don't get any marks. So the next one is 1.66 and 1.51. So 1.66 is here. 1.5, 1.51. We then have, next one is 1.74, 1.40. So 7.4 is going to be here, because that's 7.5 equal to 2. There's going to be 0.01. So 7.4 is going to be about there. And 1.40, so 1.40, it's exactly there. Notice, sorry, that went off the top there. Notice, by the way, that I'm using small crosses, a sharp pencil. If you're using a fat pencil, you're doing blobs, you lose your mark. You don't get the mark for the graph. Sharp pencil, small crosses, they've got to either be that, like that, or they have to be a dot with a circle. Personally, for the graphs with range bars, I would say a cross is a lot better, a lot more useful to you. So anyway, so we're going across 1.81 to 1.30, so 1.81 to 1.30 is about there. And then we got 1.25, no, hang on, 1.86, sorry, so 1.23, so 1.86 is there, oops, is about there. That's going to be 1.2, 1, 2, 3. and the next one is going to be 1.90 and 1.15. So 1.90, 1.15, there it goes. So then you've got to draw your line of best fit, and it should have approximately half of the points above and below the line. Okay, now I can tell just by looking that this is actually more of a curve than it is a straight line. But I'm being very careful to try and assess my line of best fit. Sometimes it helps to take your ruler and just put it that way round, so that you can count the number of points above and below the line. So I'm going to put my ruler about there. I think I've got 2 points below the line, and I've got 1 point above the line, so it's not quite there yet. Well, there's one thing I've forgotten, and that's to put my range bars, and that's why it's difficult to draw a line of best fit. So my line of best fit, my range bars are going to be, well, for the first 3 points there was 0.01. okay, so 0.01 is going to be 2 small squares. So I'm going to draw my range bars, each one for the first 3 as 2 small squares. Now once I've done my third one, these next 3 are going to be 4 because the uncertainty is increased. So I've got to put double-sized error bars on there. So it's not 0.01, it's 0.02, like that. And you just got to have the patience to put them on as accurately as you possibly can. Okay. Then you start thinking about your error bars. Now there's a couple of different ways of doing your line of best fit. A couple of different ways of doing it. One is to actually look down the points, and you can actually see a trend. I think personally this is probably a curve. I actually don't think this is quite correct, but if you think about it, your line of best fit should fall within all the points of your range bars or your error bars. So if I draw my line of best fit a bit like that, I've got 1, 2, 3 points above the line, got 1 on the line, and then I've got 2 below it. So I could almost get away with it. I think if I just moved it up a teeny bit on this side, and I think I'm probably closer to the truth. I reckon around about there is probably going to do it. Personally, it takes a little bit of perseverance, and it isn't, you know, and it's one of those things you just you get the knack for doing a little bit, you know, more than anything else. It's a bit of a knack to it, but you have to kind of sort of estimate a little bit. See, I think that is probably closer to the truth there. So that's my best line of best fit. It's not brilliant. Then you want to do a worst line of best fit. Now, worst line of best fit is a little bit of a balance. It's the worst possible line of best fit that goes through most of your range bars. So here I'm going to ignore that last point because I actually don't think it's correct. I think, if truth be told, I think I probably don't really trust it. It's probably anomalous. But if I've got my range bar there, if I'm measuring it like that, then I'd want to put on my worst line of best fit. I'll draw it as a dotted line, okay? So you can see the difference. And I mean, even though it's obvious what the difference is, I'm going to label them. So, because you know it's going to want to determine the line, you know, sort of best and worst acceptable line of best fit. So you want to measure the gradient of both. It's always going to ask you, In fact, it does tell you here, determine the gradient line of best fit, include the absolute uncertainty in your answer. So all you've then got to do is measure it, measure the gradient, and it's the same rule as you've always had to follow whenever you've been measuring gradients. You are drawing a very large triangle. It's got to be more than half of the page. It's got to be more than half of your area of your graph. Big triangle for your best line of best fit. Doesn't matter if you make mistakes with it, you can always rub it out because you're using pencil. I'm just going to make it clear what these points are. Now, the bit that people forget is the fact that this is a negative gradient. Don't forget. But we still follow exactly the same rules. I'm going to call this Y1 and Y2. So Y1 and Y2, well, Y1 is 1.595, Y2 is 1.215, 1.215, and we know that x1 minus x2 is going to be a negative number. So x1 is 1.6 and x2 is 1.858687. So we do our quick gradient calculations first of all. So we know that the gradient's delta y over delta x. So we do our best and we do our worst. Okay, so the best is going to be y1 minus y2 over x1 minus x2. So it's 1.595 minus 1.215 divided by x1 minus x2, 1.6 minus 1.87. Well, if you do the sum in between first of all very, very quickly, that's going to be 0.38 divided by minus 0.27, which is going to be about 1.41. I'm going to put the negative in there. Okay, and the worst line of best fit, well, that's going to be the gradient of your worst line of best fit. So again, we're just picking convenient points. Let's have a look at where it goes through. I think there's a nice one there. It's not perfect, but it'll do. And there's a nice one just there. And we literally just then put the arrows on. Now this one with the worst line of best fit, you've already demonstrated your ability to be able to measure a gradient accurately. So you know what? You don't have to go into quite so much detail with this one, but it's still worth measuring it and writing it on the graph paper. Why? Because it just makes it easier. So that's 1.845. This value is obviously 1.6. This value is 1.25, and this value for y is 1.575. So to get our worst line of best fit, it's going to be delta y over delta x, so 1.575 minus 1.25. Divided by the delta x, which is going to be 1.6 minus 1.845. I'm just going to make that really clear that it's separate. Okay, so your best and your worst. So your worst is going to be So that's the difference, 1.6 minus 1.845 gives me minus 0.245. So 0.325 divided by minus 0.245 gives me minus 1.3265 something or other, so 1.33. okay, so that's my formal gradient, that's my correct gradient if you like, and that's sort of the most out it could possibly be. So to actually look at the uncertainty in it, well, we're just going to double check first of all. My line of worst line best fit is shallower, expecting a smaller gradient. It's always a good thing to check quickly. So to get my uncertainty in the gradient, that's going to be the difference between my middle value, my correct value, and my incorrect value. So that will be 1.41 minus 1.33. Gives me 0.08. So my gradient is 1.41 plus or minus 0.08, and that should give you the best sort of possible estimate of your uncertainty. Right, nearly there. That's the hard bit done. So now it's got to do a little bit of playing with numbers. So we've drawn our graph, measured our gradient, all looks okay, all the labels are alright, everything's alright, good, jolly good. Last bit, and you've got that lovely bit of text at the bottom that tells you it's done. It says determine the y-intercept of the line of best fit. Include your absolute uncertainty in your answer. So this is not going to be easy. We're using y equals mx plus c. And want to find c. So what have we got to do here? We've got to find out what c is from the values of y and x. Okay. So we know that c is equal to, well, it's y minus mx. So what you could do is measure your values of y and x. Okay. So to find out my actual value, I would find a value of y and x on my graph. Always well worth going back to. So if I pick a nice easy value, now what I'm going to do is I'm actually going to pick the same y and x. I'm going to pick the point where they cross. It's a little bit of a cheat. Actually, am I confident in doing that? Not really, actually. So what I should do is pick something that's a nice convenient set of values. Well, if I pick this one here, so my x is always 1.7 and my y value is there. So my correct value for y here is 1.454 versus 1.7. So for my correct value would be 1.454 minus my correct value for my gradient, which is 1.41. Okay, and multiplied by my value for x, which is going to be 1.7. So that's pretty trivial. So my y-intercept would come out to be, now I've got to use a standard calculator unfortunately because my Scientific One battery on it's just run out. So we can start with 1.41 times 1.7. That's going to be 2.397. So we have 1.454 minus 2.397. 397, and I get a negative number. Hang on, that can't be right, because it's a negative gradient and there's always positive numbers, so it can't be a negative intercept. The thing I've done wrong there was I've forgotten that it's a negative gradient, so got to put the minus in. It's the same as adding it, so it's 1.454 plus 2.397 gives me 3851. So that's hang on, 3.85 to three significant figures. Okay, so that's my y-intercept. Now I want to find, that's the best. Now I want to find my worst. So I'm going to find, I think we'll go for my lower bound. Reason being is I know that it's going to measure the intercept to be as low, but I want to see how low the intercept can actually go. So if I think about it, my lower bound for this, well, that's going to be y equals mx plus c. So the worst value,
end of period 5.
Sorry about that. So the worst value is going to be my value for y, which on the dotted line is actually going to be 1.45 minus mx. So the gradient I know is going to be less. It was negative 1.33 multiplied by the value for x, which is the same for all of them, 1.7. So that'd be 2.261. That's a negative, of course. So that would be 1.45 plus 2.261 gives me exactly 3.71. Okay, so minus 3.85 gives me a change. So 3.85 minus 3.71 gives me 0.14. So it's plus or minus 0.14. Okay, it's as easy as that. It's actually not that hard, is it? It then says use your answers to A, C3 and C4 to determine the values of P and Q. Well, that's easy. We know about Q because we said at the beginning that the values for our intercept, our values for our gradient were Q, and our value for the y-intercept was the log base 10 of P. So we know that Q is simply the gradient. So we go back and find our gradient. It's somewhere back in your paper. How far back? It's miles back, miles and miles and miles. So here we are, gradient 1.4, and so P is 1.41 plus or minus 0.08. Easy. And you then want to find what Q is. Well, if you know that the intercept is equal to the log base 10 of Q. Have I got that the right way around? Go back. Yes. No, log base 10 of P. Sorry. Got that the wrong way around, haven't I? Have I got that the wrong way around? Gradient's Q, so it's that one. Hang on. You make a mistake, just put a couple of lines through it. Okay? Why? One, people spend ages scribbling out and trying to sort of, say do not mark this and stuff like that. Examiners know if you put a cross through something, they don't mark it. Also, if you put a couple of lines through and then you realise you had it right all along, you can write it out again because you saw what you wrote. Okay? So, oops, intercept is log Q. So the y-intercept is going to be 10 to the power of the intercept is going to be equal to Q. Okay, that makes sense? Yeah. Okay, so we want to find out what the intercept is. The intercept is 3.85. 10 to the power of 3.85 equals Q, and we can work that out. And then the next one, to work out the worst one, we'd basically be using a value 3.85 plus 0.14, so 10 to the power of 3.99. Gives us our worst value of Q. Okay, and you just work them out. I'm going to go and get my calculator and work out what those logs are. Bear with me. Right, so having calculated the 10 to the power of those values, we know that P is going to be, well, the log P was the intercept, then it's the 10 to the power of the intercept, which will be 10 to the power of 3.85, which is 7, well, I'm going to say 7,000, it's 7,779. I think I'd have to say 7,100 or thereabouts, okay? Which you would then say is going to be plus or minus, well, the difference between the two, we just work it out. You just say, okay, 9772 minus 7079 is 2693. So that would be 2,700. And that then gives you your value. Okay, pretty simple. It then says, use your answer to determine the temperature at which the viscosity of the cooking oil is going to be 0.1 pascals seconds. So this time we've got to rearrange the equation, haven't we? Let's have a think. So where are we going to do this? So if we look at the equation that we've got, we know that the log, okay, the log of the viscosity is equal to log of P plus the log of Q times the log of theta. So we need to try and find this. So it says, is this going to work? Well, let's think about it. What we want to be saying is actually we want to find out what log of theta is first, yeah? So the natural log of theta is going to be, well, natural log of theta is going to be equal to, well, it's going to be natural log of the viscosity minus the natural log of the constant P divided by Q. So, oh my goodness, this looks awful, doesn't it? Okay, but basically you're substituting in numbers. So you're finding out what that is, and then you could take some red values. You could do it that way, but really we want to use, it says use your answers to D, so it wants you to find it using P and Q. So you've got your values, they're from the gradient. You could just rearrange Y equals X plus C and use gradient and intercept, but this way is probably going to be easier. So we want to find out what log base 10 of the viscosity is, and we need to find the log base 10 of the constant P. So we just find those and we substitute. Okay, so substituted, and we want to find out if this works. So all we're really doing is we're just substituting in numbers. The examiner's not after the answer here. Notice they're not wanting to know the uncertainty. How do we know? Well, for starts, there's only one mark. The second clue is they've not asked for it. So it's going to be -1 minus 3.85 gives you -4.85 divided by 1.41 gives you minus 3.4. Okay, So negative 3.4 degrees Celsius. Okay, and that's the answer. Now it doesn't matter. It doesn't matter what your actual answer is, I don't think. I think what actually matters, what the examiner's looking for there, is the substitution. So to summarise, what do we need to know about doing question 2? Well, question 2 is always the same. The first thing you're always asked to do is to put it into a format of y equals mx plus c by rearranging whatever they've said goes on the y-axis and as a subject of the equation, trying to separate out the x in there, so you've got a constant multiplied by that, and then you look at the intercept and just compare it. Always do CF y equals mx plus c. Do that every single time underneath your final formula. It'll start to make sense. Then whatever's above m is your gradient, whatever's above c is your intercept, and you get the mark. They'd asked you always to work with values in a table. You should always try to estimate the uncertainty. There are lots of different ways of estimating uncertainty. Go for whichever one's easiest. In this case, it's easier to work out the upper bound and know it's the difference between the upper bound and your value gives you an uncertainty. Okay. What the examiner actually puts in their mark scheme is they give you a range of uncertainties that they think is most suitable. Then you draw your graph. You draw your graph using range bars across to denote where your actual point is, and then a range bar to show your maximum and minimum bounds. You draw your best line of best fit, you draw your worst line of best fit, you measure the gradient of both of them. Once you've measured the gradient of both of them, you work out the gradient of both of them. The difference between the two is the uncertainty in your gradient. So you take the gradient of your best line of best fit, and then you take the grade. You look at the difference between that gradient and your worst line of best fit, and basically that uncertainty is the difference between the two. Then you basically determine the gradient. You might get asked some kind of question. This is the unpredictable bit, but it's always pretty much the same. You've got to do a calculation and then use an upper or lower bound, work out the difference between the value calculated using your upper or lower bound to work out what your uncertainty is. It always asks you, it tells you include the absolute uncertainty. You must include it or you don't get the marks. Okay, then you must compare it with your y equals mx plus c formula from the beginning of the question and work out what the intercept is. Use the intercept or the gradient, and you've got to do some kind of calculation, and it wants the absolute uncertainties in your answer. So again, upper and lower bounds always. Okay, so always compare it with your upper bound or your lower bound for your best and your worst value. And then you get asked to do some kind of clever thing with logs, usually some kind of calculation, which is actually usually easier than it looks. And that is the second and last question of paper 5. That's how you do paper 5. So now you've had a go at that. You've looked back at your paper 5 that you've just done. You've compared it with the methods I've shown you. Your numbers will be different. It doesn't matter. It's the technique that actually makes the difference here. So what you need to do is just make sure that your value, that your techniques are being used. So you're going to get another paper 5 shortly, and this time I'd like to do it under exam conditions. But go through this, watch this video again. I know it's long, but watch it carefully. Make sure you haven't missed anything silly. It's very easy to miss out bits. Most 99% of doing paper 5 is about technique. If you learn the techniques, you can fly through this paper and score brilliantly on it. It's easy money. It's low-hanging fruit. Whatever cliche you want to attach to it to say it's easy, yeah, it's an easy win. Whatever it is such an easy way to bump your grades up. Okay, so follow the techniques. Go back, watch the video again. Pause. Think about what I did. Not just copying it down directly, but think about the techniques I used. Okay, right, enough from me. It's time for you to now go through your paper and do your corrections and see whether or not you got it right, and also see if I made any deliberate mistakes, because you know I do.